It's time for Astronomy in the News. I am Astrobit, also known as Brian W. Mulligan.
And I am MC Hammer, also known as Sam Factor. And here are the astronomy news stories from this month. So, buckyballs have been found in space. What are buckyballs, you might say? Well, this is a picture of what they look like. They are 60 atoms of carbon that are arranged kind of in the shape of a soccer ball in a sphere. They are the largest known molecules in space. Their full name is not just buckyballs. They are Buckminster Fullerene, named after a architect, I believe. Mm-hmm. So this scientist here, Dr. Martin Cordner, has used the Hubble Space Telescope, a new observing technique, to get very high resolution, very high sensitivity observations of 7 stars that show interstellar absorption, so clouds of gas and dust in between us and those stars, as well as 4 control stars to compare them to. And they detected a bunch of absorption lines caused by these giant molecules. So this is not the first time that buckyballs or Buckminster Fullerene has been detected, though it is the most conclusive. They found it in 2012 and in 2010. But this study really found those very precise lines, and they compared them to lab experiments, not only in their wavelength, but also the ratio of their strengths, and found that conclusively this was Buckminster Fullerene. And this will hopefully continue to inform us on the kinds of chemistry that happens in these clouds, and similar types of observations with this new technique will enable us to figure out there are a bunch of interstellar absorption bands, they call them, that we don't actually know what they are, but observations with this technique hopefully will help us figure out what they are.
Okay, so observations of the sun by a team led by Emily Mason of Catholic University of America have revealed the first direct evidence of rain on the surface of the sun in coronal loops. So, of course, this isn't rain as we know it. Instead, it's plasma that's heated up on the surface of the sun, probably through magnetic heating. If you have an induction stove, you might be familiar with magnetic heating. You put a pot on the stove, it uses magnetic fields to heat the pot. There's no element or anything like that. So potentially similar heating technique. The plasma heats up and rises as it cools, and then you can see it falling back down. As it reaches the top, it cools off, it condenses just like rain does on Earth, and then it cools and falls down and becomes rain. Of course, you probably aren't going to want to run around in this rain. The hot plasma is about 1 million degrees. The cool plasma is only 10,000 degrees. And when it falls, it's falling at something like 150,000 miles per hour. Hard rain. However, the individual droplets are awfully wispy compared to the rain on Earth. They're kind of like little clobs of gas that are very low density, but still, you probably don't want to be hanging out there. The rain of this kind has been known about for some time, but the mechanism by which it occurs has been a little uncertain, and it wasn't sure whether it would occur in loops such as this or how frequently it occurred. This study demonstrated that such rain is extremely frequent. They basically looked at 3 different loops and found this rain happening in all 3 of them. These observations are going to help understand the details of the source of the rain, and is also going to help understand how the corona of the sun becomes as hot as it does.
Cool. So, next up, some really old data helps us figure out what's going on the moon. So the Apollo missions back in the 60s placed a bunch of seismometers on the surface of the moon. And they actually lasted for about 10 years between 1969 and 1977 and detected about 11,000 very deep moonquakes on the moon, which at the time they attributed to the kind of reflexive tides, how the moon excites tides in the oceans of the Earth also excites tides on the moon. And they attributed those earthquakes to the core kind of shifting around with tides. But this new study used more modern algorithms to analyze that same data and connected it to some very recent imaging from the Lunar Reconnaissance Orbiter, which is this picture right here, taken around 2012, and connected some of the more shallow moonquakes that were detected by these seismographs to actual fault lines that were imaged, as you can see where those arrows kind of follow this crack down. And what this is indicating is that the core of the moon, or the moon itself, the whole moon, is cooling down. And as something cools, it shrinks, and the core is shrinking, and the surface of the moon can't really shrink with it. It can't go anywhere. So it creates these fault lines. It can't like wrinkle up like the surface of a grape. So instead it breaks and makes these faults that you see. So this will hopefully help us figure out more about the moon's structure inside and our own history between the Earth-Moon system.
Okay, a team led by Weiston Binbo of the Center for Astrophysics at Harvard have used a novel method to measure the diameter of a couple of stars. So the team made use of asteroids within our own solar system. As these asteroids pass in front of distant stars, the light of the star is diffracted by the edge of the object, at the edge of the asteroid. They look for very short period brightening and dimming of the star, and they use this to determine how big the star actually is based on its distance. So this is a very challenging observation. A very large telescope is required in order to pick up enough light from the star to image it very rapidly. So they used something called the Veritas telescope. The Veritas is a pretty good sized telescope. You might be familiar with telescopes such as the Hobby-Eberly telescope at UT Austin. It's a pretty big telescope, but it is not designed around the idea of taking very frequent images of a star. It tends to look at a star for a few minutes or tens of minutes or something at a time, not for very short periods of time. So Veritas, however, is telescopes that are normally used for looking at cosmic rays hitting the upper atmosphere and causing a brief flash of light. So they're very large. They they gather a lot of light, and they look at light. They sample the light that they're receiving really frequently. So this team basically was taking images of this star or gathering the light from the star, seeing how bright it was, hundreds of times per second, and watching as the asteroid passes by. You see these rings around the background star, and as they'd see the asteroid passing these rings, and as it passed those rings, they detect the very small changes of brightness as it passed those rings. The details of exactly how that occurred give details about about what the size of the star is on the sky. So the team observed two stars using this method. The first was found to have a size of about 11 times the size of the sun. This is a star that had previously been suspected to be a red giant, and basically it said, yes, this is definitely a red giant. This is a really big star. The other one that they looked at is only a little over 2 times the size of the sun. That's pretty big in our terms, but we have never actually managed to determine the size of a star that small. Normally, when we determine the size of stars, we need them to be really, really, really big in order to measure their size. They have managed to reduce the size of stars that we can see by a factor of 10 using this new method. So this is extremely exciting. It's going to be extremely helpful to calibrate a lot of the other methods that we use, something called interferometry, where we look at stars and assume that stars are just points on the sky. This team is going to be able to say, yes, the star is a point, or no, the star is too big to actually be used for that method. So they're probably going to be imaging tens or hundreds of more stars in the next year, and this is going to very much improve the quality of astronomy overall.
This is a really cool story. So, Gaia, which we heard a little bit about in the first talk, is a European Space Agency mission designed to very precisely measure the positions and distances and motions of about 1 billion stars over the lifetime of the mission. But kind of as a side effect, because they're observing the entire sky, they also see asteroids, which are much closer. And so the Gaia mission has observed about 14,000 previously known asteroids, which is what is shown in the red on the left side. So the near-Earth asteroids, the ones that come relatively close to the Earth, nothing too dangerous, are shown in yellow here in the center. The main belt asteroids that you've all heard of in between Mars and Jupiter are in orange. And then there's this special kind of family of asteroids called the Trojans, which follow around Jupiter. Those are shown in the dark red, way on the outside. But this new story is that Gaia has detected 3 never-before-seen asteroids, which are shown in the white, that happen to be in a very tilted orbit around the sun. They're greater than 15 degrees outside of the plane. And normally these things would be very difficult to find. Most asteroid surveys tend to look in the plane of the solar system because that's where most asteroids are. And these highly tilted asteroids don't spend very much time there, so they're hard to find. But since Gaia looks at the entire sky, it's an unbiased survey, and so it found them. And hopefully these things will, with more statistics, when we find more of them, we'll be able to see different populations of them and figure out potentially more information about how our solar system formed and the dynamics of how it evolved and is still evolving.
All right, our last story is Astronomy Not in the News, where we cover research that's generating discussion within the astronomical community but hasn't necessarily made it into mainstream news sources. This month's story is about a catalog of galaxies created by a group led by Rin Suas of UC Berkeley. On a sort of local note, Sam, I don't know if you remember, I forget whether it was your year or the year after, Rin actually considered graduate school here at UT Austin. But ultimately decided that UC Berkeley was a better fit for her. We won't hold it against her. She's doing great work anyway. But Rin's work was focused on measuring the density and color gradients in distant galaxies. So most studies of the sizes of galaxies focus on the light that the galaxies give off and kind of define how big a galaxy is based on where the point at which half the light gets half as bright as it is in the center of the galaxy. Instead, Rin used the brightness as well as the colors of galaxies to measure the point at which half the mass of the galaxy is contained. So a way of kind of measuring the mass density of galaxies instead of a light density of galaxies. So she published the first catalog of 7,000 galaxies that provide this information. Some of the interesting findings of her research include that galaxies that are forming stars and galaxies that aren't forming stars, so-called quiescent galaxies, they look remarkably similar in terms of their density based on her measurements. it seems that the density is more a measure of the mass of the galaxy than it is what type of galaxy that you've got. This is a little bit unexpected because the what's called the half-light radiuses, the light density of these galaxies can be very different between the two different types. And they also found that the growth of galaxies that are quiescent, that aren't founding stars, can almost entirely be explained by the galaxies, or by dwarf galaxies merging with the larger galaxies. So that these quiescent galaxies aren't growing necessarily by adding more stars, they're growing by having other galaxies fall into them and get, absorbed and eaten up by the main galaxy. So this is a somewhat unexpected result. It'd been kind of confusing exactly how these quiescent galaxies grow. Their future work is is seeking to understand some of the differences between the quiescent and star-forming galaxies at the lower mass end of the range. But it's an exciting new methodology and confirmation of a few different techniques in order to do these measurements. All right.
Thank you very much.